Welcome. In this video, we're diving into the crucial ethical considerations surrounding big data. Big data refers to extremely large data sets that are analyzed computationally to reveal patterns, trends, and associations, especially relating to human behavior and interactions. We will explore the importance of privacy, fairness, and responsible use, which are some of the critical pillars that ensure big data is used for good and not for harm. Let's begin by addressing privacy challenges in big data, focusing on data collection and how we protect personal information. One of the primary concerns is the massive collection of data, often without explicit consent from individuals. Another challenge is the re-identification of anonymized datasets, where seemingly anonymous data can be linked back to specific individuals. Furthermore, the increasing cross-platform data linking and profiling, and the general lack of transparency in how data is used are serious concerns. To address these challenges, we need informed consent mechanisms that clearly explain how data will be used, data minimization principles, which is collecting only the data that is needed, strong anonymization techniques to protect identities, and giving users greater control over their personal data. Now, let's explore the technical approaches for data protection. Anonymization is a key technique, and here's how it works. First, remove direct identifiers such as names, social security numbers, and email addresses from the dataset. Next, generalize values to make it harder to pinpoint specific individuals. For example, round ages to the nearest 10 and keep only the first 3 digits of zip codes. Another method is differential privacy. This is a mathematical framework that quantifies privacy protection by adding controlled noise to the data. For example, we can add random noise to the result of a query. This ensures that the presence or absence of any individual in the dataset does not significantly affect the outcome. Now let's shift our focus to bias in big data. There are several types of bias that can creep into data systems. Selection bias occurs when the data sample is not representative of the population. Confirmation bias happens when we seek out data that confirms our existing beliefs. Historical bias arises when past inequalities are reflected in the data. Algorithmic bias occurs when a model amplifies existing biases. The sources of these biases include incomplete or skewed datasets, human prejudices in data collection, socioeconomic disparities in data access, and technical limitations in measurement. Recognizing these sources helps us mitigate bias more effectively. Let's consider algorithmic fairness and equitable outcomes. There are several key metrics to achieve this. Demographic parity aims for equal positive rates across different groups. Equal opportunity seeks the same true positive rates for all groups. Individual fairness means treating similar individuals similarly. Counterfactual fairness ensures that decisions would not change if sensitive attributes were different. There are several ways to implement fairness. Pre-processing involves removing bias from the training data before it's used. In-processing involves constraining algorithms during training to prevent bias. Post-processing involves adjusting model outputs to ensure fairness. Continuous monitoring and regular bias auditing are essential for maintaining fairness over time. Now let's look at the frameworks and best practices for ethical data use. Several frameworks guide responsible data governance. The General Data Protection Regulation, also known as GDPR, is a European data protection regulation that sets standards for data processing and protection. The FAIR principles, which stand for findable, accessible, interoperable, and reusable, promote the sharing and reuse of data. The Institute of Electrical and Electronics Engineers, also known as IEEE, standards provide ethical design guidelines for technology. AI ethics boards are organizational oversight committees that ensure ethical practices are followed. Best practices for responsible data governance include establishing clear data usage policies, conducting regular ethical impact assessments, transparent data collection practices, and engaging with stakeholders to gather feedback. Now let's explore the practical steps for ethical big data deployment. Before collecting any data, Conduct a thorough ethical risk assessment to identify potential issues. Implement a privacy by design architecture, which means integrating privacy measures into every stage of the system. Establish bias detection and mitigation protocols to identify and correct biases. Create transparent reporting mechanisms to ensure accountability. Here is a simplified example of how to check for fairness in a machine learning model. The function check fairness takes a model data and a protected attribute such as gender or ethnicity as input. It calculates the average prediction for each group defined by the protected attribute and returns the results. This automated monitoring helps ensure that the model is fair across different groups. Let's look at the emerging challenges and evolving solutions for ethical big data. One challenge is AI-generated data, which raises questions about synthetic data ethics and authenticity. Quantum computing introduces new encryption and privacy paradigms. The expansion of the Internet of Things, also known as IoT, brings ubiquitous data collection concerns. Cross-border data flows create international governance complexity. Evolving solutions include dynamic consent management systems that allow users to control their data in real time, real-time bias monitoring and correction mechanisms, federated learning for privacy preservation, and the harmonization of global ethical standards. In conclusion, ethical big data requires continuous vigilance, adaptive frameworks, and collaborative governance to balance innovation with human values. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.